Okay, so in this overall topic of permutation and combinations, or perms and combs, this topic is really concerned with solving these seemingly simple counting questions. So what we mean by counting questions are just these questions. These questions that simply ask how many. So for example, how many 4-digit passwords are possible? We got 3 people and we're trying to put them into a line. How many ways can we do so? We're gonna go to a standard deck of cards. I'm gonna ask you to draw 5 cards out, and how many ways of actually doing that? Or we are selecting 5 pieces of chocolate and there are 3 flavors to choose from. How many ways can we achieve this? Okay, so this is a really important thing going to the whole topic. Basically, how we're gonna approach each one of these questions is gonna be dependent on 2 characteristics of the situation. So for each one of these scenarios, we're gonna ask, these 2 questions. We're gonna wonder whether repetitions are allowed in these situations, and whether or not order is significant behind these situations. So we're going to look at these situations and look at the answers to these 2 questions. So let's examine the password one first. Okay, so we're trying to do a 4-digit password. And firstly, are we allowed to do repetitions in this scenario? Well, yes, because you can choose a really silly password like just 4 ones. Okay, so reselecting a digit to be used, or in other words, having repetitions, is allowed. And is there a sense of order in this scenario? Well, definitely, because if your password is 1, 2, 3, 4, or if you start shuffling the order, like the order is backwards, this is definitely considered to be a completely different password. So it constitutes as a different arrangement. So in this sense, order is certainly important. Okay, let's look at the next one. What happens if we try to arrange 3 people in the line? So suppose we got 3 people represented like this, so person A, person B, person C. And you try to put them into a straight line, and again ask ourselves these 2 questions. Are repetitions allowed? Well, the answer is no, because this scenario cannot occur, right? So basically in this whole entire topic, when we look at people, okay, we're going to assume that people are always unique. Everyone's an individual. So you can't possibly have this outcome, right? Because we assume there are no clones, okay? There are no clones when we deal with people in this topic. So you can't have a repetition of having 2 of the same people. So no repetitions is possible in this scenario. And well, is order important? Of course, because you're forming a line. It's a queue, right? So who's in front of the line? If it's a different person, we consider this to be a different line. So there is a sense of order. And order is important. Okay, next one. So we're gonna look to draw 5 cards from a standard deck. Is it possible to see repetitions? No, because each individual card in a standard deck is completely unique. So you cannot have like 5 aces that are clubs, right? That's not possible. So no, there are no repetitions in this scenario. And well, is order important? No, because in card games, right? Like if somebody deals you like 5 cards and you get these 3 aces and these 2 twos, if it arrives to you in this order and you just happen to hold the cards in this order, or okay, maybe in a slightly different scenario, you're dealt the same cards but in different order. They just show up to you in a different order. But like it doesn't matter, because in the end you have 3 aces and 2 twos. Like you don't care for the order in which the cards arrive in your hands. You just play them and you just acknowledge what cards you have. So as you're holding cards when you're playing a game, there is no sense of order. So in other words, these 2 hands are considered to be the same. Order is irrelevant. Okay, lastly, okay, so we go into a shop, and the shop offers 3 flavors, and you have to choose 5 pieces of chocolate, nominating the flavors you want. Repetition is allowed, definitely. If you have a favorite flavor and you can just repeatedly choose all 5, you can just choose 5 of the one flavor. So you can repeatedly choose one of them. So repetitions definitely are allowed. And is the order important? No, because after you chose the flavors, it doesn't matter which order you say the flavors in the end, you're going to get the same type of chocolates. It doesn't matter which order they arrive at, right? So no, order is not important. Okay, so hopefully you got a sense of how to interpret these 2 questions for each of these scenarios. And yeah, this is important because the answers to these 2 questions will control how we're going to approach answering these questions in the first place. Okay, so yeah, with these answers to these 2 questions, there are all in total 4 scenarios, right? So for example, repetition not allowed, and then order is important. And this scenario has a special formal name, and that's called a permutation. And a combination for this scenario, where there are no reps, and order is not important. I'm not sure if these 2 other possibilities in these 2 scenarios, I'm not sure if they have actual formal proper names. I don't think they do. But regardless, this scenario here, I think outside of very few extremely challenging questions in exams, this scenario does not come up at all, and it's certainly not a regular thing in the syllabus. So we won't touch upon this scenario much at all. This scenario is the easiest one out of all of them, and yeah, I'm not sure if it has a formal name or not. Okay, in this video, we're gonna look at these 2 scenarios, starting with this one, the simpler one, and then we'll go on to permutations. Okay, so we're looking at making choices under these 2 assumptions, okay? So we got 3 objects in front of you, 3 unique objects, and I'm asking you to get 2 of them out, okay? So out of these 3, I want you to go get 2 of them, while under the assumption that repetition is allowed and order is important. Okay, so one possibility you may choose is AB. But then order is important, so you could have chosen BA, so that's considered a different outcome to that. So you should consider both of them. And then now you can choose AC, and then do the flip of AC, because order is important. We did AB, AC, so the last possible pairing is BC, and then its mirrored image. Well, this is not the full complete possibilities of the list, right? Because we're saying repetition is allowed, so you could have gone for double A, double B, double C. Okay, and that's it. That really is the full list. There are 9 ways of doing so. So 9 ways of going to 3 objects, grabbing 2 of them under these 2 assumptions. Okay, so obviously you don't want to get at this answer of 9 like through actually listing, right? That's just too slow. Like if there are tons of objects, more than 3, you're not going to produce this list by hand, right? So there should be a faster way of getting to this answer of 9, and here's how you do it. Okay, it's the same question. So what you can do is just draw up 2 slots representing the 2 selections you got to make, and then just ask yourself, when you're trying to make the first choice, how many options do you have? You can choose from A, B, or C initially, so you got 3 options. And then because repetitions is allowed, when you're trying to make your second selection, there are still 3 options available to you. You can still choose A again, or B again, or C again. So you got 3 options each time, and then you multiply these 2 options together, and you get the 9 that we wanted. So you can get an answer quickly through this, not just listing everything out. So you can just do this to a simple multiplication of the choices available, basically. Okay, so this is just summarizing that concept we just saw, but let's say you got n objects, okay, rather than just 3. And then out of these n objects, I want you to grab r of them. Yeah, under the 2 assumptions we mentioned earlier. And what's going to happen, when you make your first choice, there are n available options, right? So you've got n options. When you go for your second choice, there's still n options. Nothing's changed because repetition is still allowed. Everything's still available to you. We made 2 choices. I'm asking you to get R, right? So altogether there should be R of these slots. There should be R of them. And we multiply and gather them. The index laws tell you that this is n to the power of R. Okay, so this is like a general formula for this situation if you like. Let's do a quick actual numerical example. So you're trying to form a license plate. The license plate has 5 characters. It's made of 3 letters followed by 2 digits. How many of these license plates are actually possible in total is what we're asking. Well, for your initial choice, first of all, repetitions are allowed. You're allowed to repeat on letters. And of course, order, there is a sense of order as you make this choice, because when letters come in different orders or numbers come in different orders, it's a different license plate. So we're definitely under the 2 assumptions we have been working with so far. Okay, but each time when you're trying to make a choice of a letter, there are 26 letters each time. So here's the initial multiplication. And now we've got to go to the same argument but with digits. And remembering that 10 digits to choose from. 1 to 9 and then 0 itself. And multiplying these numbers together, we get almost 2 million choices. Okay, so that was that simple scenario where repetition is allowed and order is important. So now we're going to go to the other one, the permutation assumption. So now we got 4 objects, and now I'm asking you to, from this 4, I want you to pick 2 of them. But under the assumption that repetition is now not allowed, but order is still important. Okay, so I want you to also make note of the following. When we do a permutation, we're going to say 4 pick 2. So the P from the pick lines up with the word P from the permutations. Okay, so this is a good way of describing these actions. So you know whether it's a permutation or combination matters. So the choice of this word here is important. So we're going to do 4 pick 2 in this scenario. And it just means we're doing that under these 2 assumptions. And furthermore, we got a notation for 4 pick 2. It's written like this, 4p2. And we're asking, how many ways can you do this? Well, here are some possibilities. So, but there are more to it. So if I selected AB, that's one possible outcome. But we're saying order is important, right? So the flip of this constitutes as a different outcome, so I should definitely list it. And I've done that for each of the ones I've written before. Okay, so notice how there's no more to this list. Like for example, what's not listed is AA. So AA is not possible because you cannot have repetitions now under permutations. So this is the full list, so you can see that 4 pick 2, the number of ways of going to 4 items, picking 2 of them out is 12. Okay, so again, we don't want to reach this 12 just by listing all the outcomes, right? Again, that's way too slow. So we want to come up with a way to compute the 12 faster. Okay, so let's do it a faster way. So we got these 4 objects, and you're trying to do 4 pick 2. In your very first choice, right? How many options do you have? The answer is 4. Like all 4 objects are in front of you and available, right? So there are 4 choices. But as soon as you grab one of these items, so let's say you grab the card A, okay, it's gone. So now as you make your second choice, because card A is gone, no repetition is allowed, right? And then so now you're left with 3 choices only. So there are 3 possibilities with the second slot. So and multiplication of these 2 possibilities gives us the 12 that we want. Okay, let's do 5 pick 3. So initially you got 5 choices. After you have grabbed the card, you cannot repeat it, so it's gone. So now you're left with 4 choices. After your second pick, you were left with 3. Okay, so here's the answer, right? But here's what we want to do. We don't want to really write a huge chain of numbers multiplying like this as our working out, because, well, imagine if there's lots of objects, right? Lots of numbers, and you're doing lots of picks. This chain of multiplication would be huge. So is there a way to compact this down into a more efficient, just writing? Is there a more efficient way of writing this? If you've seen factorials, you can see that this may have something to do with factorials, okay? So we can write maybe 5p3 in terms of 5 factorial first. But 5 factorial is descending all the way down to 1, right? So we only want 5 times 4 times 3, so we only want this bit. And we want to throw away this red bit, right? That's not part of our working out. We want to get rid of it. So therefore, you write 2 times 1 on the bottom of the fraction to cancel it. So now you can see that you can represent this chain of multiplications through a more compact factorial notation like so. So 5 factorial, and then dividing by this extra 2 times 1 that you did not want, okay? So 5p3 is 5 factorial on 2 factorial. Let's just illustrate this pattern, but with slightly bigger numbers. So here's 8p5, right? So 8 descending up to 4. Again, try to express this in terms of an 8 factorial, right? Look like this. What we really want is this blue bit. We want to throw away this red bit. So therefore, we go to this 8 factorial that has too much stuff, and then we're going to go to the bottom and divide by 3 by 2 by 1. But this is nothing more than 3 factorial. So 8p5 is 8 fact on 3 factorial. Okay, so we derive these two things for these two specific examples. Can we maybe generalize this into a formula? So what's happening? We do 5p3, it's basically this number factorial on top, and there's another number factorial on the bottom, and this number comes about from the difference between these two numbers. And you can see that it holds for this example too. So therefore, we do in a general case, right? So NPR. So the top is just this number factorial. The bottom is also just some number factorial, but that number is the difference between these two. Okay, so this general NPR formula is called the permutation formula. And it simply counts how many ways can we go to n objects and pick out R of them, with the assumption that there's no repetitions and order is important. Okay, just a quick word about how to access, how to do NPR on a calculator. So on a calculator, you can see the NPR function right here. So you can see that it's access to shift and then the multiplication button. So let's say if you want to do AP5, you actually type the number first, type the initial number first, so put in 8. And then shift times button to access the NPR function. And then you type the second number that comes afterwards, and then just press equals. And you should get this number. Okay, so we can do NPR for any number R, right? That's less than or equal to n. We're going to look at the scenario where this number that we're choosing is exactly the same as the initial amount. So for example, we're going to do 3 pick 3. 3 objects available, we're going to pick 3. Again, we're under the assumption, so the number way of doing this is actually not 1, because you have to keep in mind that there's a sense of order, right? But here they all are. First of all, 3p3, okay? We're doing 3p3. And then here's listing all the outcomes. So you can see that if you list all the outcomes to 3p3, you can see that it's basically asking how many ways can you rearrange 3 objects. Like I'm just taking all 3 objects and look at all the ways that I can actually just shuffle and rearrange them, okay? So 3p3 is number way of arranging or shuffling 3 objects. This phrasing of shuffling 3 objects will come up a lot in this topic. Okay, so first of all, the answer to 3p3 is what? It's 6. There are 6 ways of doing this. How do we get to the 6 quickly? If you try to do 3p3, okay, so from these 3 objects, you have to choose one initially, right? So right in the beginning, there are 3 choices. You choose one, no repetition, so it's gone. So now you're left with 2 choices, and then third choice you're left with 1. So this is where the 6 comes from. And you can see that it's actually nothing more than just 3 factorial, giving us 6. So in general, when you try to do NPN, what's going to happen? You're going to have n choices right in the beginning, and then you lose a choice, and then you lose a choice, and you keep losing until you descend all the way down to 1, exactly 1. Because there are n objects overall, you're trying to make n choices. If there are n choices, that means there are n of these slots, right? If there's n of them, the last number here must be 1 itself. So you can see that this is just nothing more than n factorial, because it starts at n and then descend all the way down to 1. So NPN is nothing more than n factorial. So and then NPN is just number way of shuffling n objects. So n factorial is the number of ways of shuffling n objects. Okay, so that was coming up with this through this type of working out. Of course, we got we got the permutation formula here that we saw early on, and of course we can arrive at the same result using this formula too. So we're gonna do NPN, right? So you just substitute R for n. You do that. So when you sub R for n, the bottom becomes n minus n, which is just 0 factorial overall. But recall that 0 factorial is 1 and not 0, okay? So this division is fine. Your n factorial divided by 1, which is just n factorial, and of course that's the result we saw previously.